Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back. This is lecture 12 of this course, Flight Dynamics and Aircraft Performance. In the last class, we discussed about how maximum rate of climb does not happen at maximum climb angle. Alright, so today we'll discuss about gliding flight. Okay, now let me ask you one question. Suppose for example, an aircraft is cruising at a certain altitude and because of some certain reason, the aircraft engines failed. All right. Now, the next thing, what will pilot do? The first thing the pilot will do, try to estimate how much is the maximum distance or horizontal distance that aircraft can travel. All right. And what should be the glide angle? Of course, the glide angle will be negative. So, what should be the minimum glide angle? What are the conditions required to travel maximum horizontal distance? So, that we'll discuss today. All right. Now, look at this figure. We have this aircraft which is climbing downwards. We call it as a gliding flight. Alright. Now we will be developing the equations of motion for this gliding flight. So this is the flight path angle gamma, which is obviously negative. Weight is acting downwards. Lift is perpendicular to the velocity. This will also be flight path angle gamma. And this will also be gamma, and similarly this will also be flight path angle gamma, and this is the drag which is acting opposite to the flight path. All right. Now here the aircraft is in a power of glide, that is thrust is 0. Okay, that's why I did not consider here thrust. Okay, for an equilibrium unaccelerated glide, sum of the forces must be equals to 0. Okay. Now, what are the forces which are acting perpendicular to the velocity? That is L equals to W cos gamma. Similarly, parallel to velocities, D equals to W sin gamma. Alright. Now, if I divide this equation, what will we get? We will get L by D equals to 1 upon tan gamma. Okay. So, I can write here tan gamma equals to 1 upon L by D equals to or 1 upon CL by CD. Okay. So, hence glide angle is strictly a function of aerodynamic efficiency, that is L by D. Okay. So, to travel maximum horizontal distance, this gamma should obviously be minimum. Okay, so we will have tan gamma minimum equals to 1 upon CL by CD maximum. Okay, now we can write here gamma minimum equals to tan inverse 1 upon CL by CD maximum. Alright. Now remember this condition CL by CD maximum? Yes, we already discussed about this condition CL by CD maximum. Yes, so we have to fly at thrust required minimum to get this CL by CD maximum. Now do we need to fly thrust required minimum so that aircraft can travel at maximum horizontal distance? Right? So we assumed in the earlier that the engines have already failed. We do not have thrust requirement over here. Okay, so let us address this question. Why do we need to fly at thrust required minimum, or does it make sense at all? Alright, so let us address that question. So first of all, for thrust required minimum, we already calculated that CL by CD max was equals to 1 upon 4 CD naught K. So please refer your notes that we have discussed earlier. Now do we need to fly at thrust required minimum? Let us address that question. Alright. Now if I have here L by D or CL by CD, okay, I can write here CL upon CD naught plus KCL square. Okay, so for maximum CL by CD, we need to do what? We need to differentiate this equation. All right, we need to differentiate above equation with respect to CL. Now, why CL? Because CL is also a function of CD. Okay, so CD is also a function of CL. Okay, so I can write here dCl by CD upon dCl equals to CD naught plus KCL square whole square CD naught plus KCL square into 1 minus CL into 2KCL equals to 0. Alright, so if you solve this equation, finally you will get CD naught equals to KCL square, that is CL equals to CD naught upon K. So here this is what? CD naught, this is 0 lift drag. So please do not forget, this is 0 lift drag and this was drag due to lift, KCL square. Alright, drag due to lift, and finally we get L by D maximum. I will simply substitute here CL equals to CD naught by K upon CD naught plus CD naught. Since we have CD naught equals to KCL square, I am writing here CD naught plus CD naught, and I get here CD naught by K upon 2 CD naught, and finally we get L by D max equals to 1 upon 4 CD naught K. Now see here also we got the similar condition, CL by CD max equals to 1 upon 4 CD naught K. So the point here to note is that this result has nothing to do with the steady level flight or thrust required minimum. It is a general result having to do with this aerodynamics of the aircraft. Okay, so it is the same result whether the aircraft is either climbing or even turning. But point here to remember is the velocity with which L by D max is achieved is dependent on such conditions. Okay, velocity at which L by D max is achieved is dependent on such conditions. Now, what are those conditions? That can be steady level flight, or the aircraft is climbing or even turning. Okay, so please remember this point, the velocity will be different when it is flying at a steady level flight or climbing or even turning. Okay, so remember what was during the steady level flight? Steady level flight, what was the velocity? So for your reference I am writing for steady level flight. Okay, so L equals to W equals to half rho V square S into CL, and velocity you can write, we have been repeatedly writing this equation. Alright, so you are well aware of these basic equations. Now, well, N by D is maximum, we have CL equals to square root of CD naught by K. So this CL will be this. Okay, so this will be the velocity for steady level flight. Now coming back to the gliding flight that we were discussing, so we can easily calculate what is the distance covered along the ground. Okay, so let me draw this free body diagram again. Okay, suppose this is the ground, this is the flight path angle gamma, of course this will also be gamma. Now what is the, let us assume this is the altitude h and this is the horizontal distance r. Okay, So now from geometry we can easily find tan gamma will be equals to h upon r, and what we need is r equals to h upon tan gamma. So if gamma is kept minimum, we will get maximum r, the distance, that is the range, r equals to r max equals to h upon tan gamma minimum. And remember, what was tan gamma minimum? This was this 1 by CL by CD maximum. So I can simply write here h into L by D max or CL by CD maximum. So this is how we can easily find what is the maximum distance the aircraft can travel in a gliding flight. Alright. Now we are discussing about fixed wing aircrafts, right? So if the engine fails, the aircraft will not come crashing down. Okay, so it will actually glide. And by gliding, how much distance it can travel? It can travel R max equals to h into L by D maximum. So it is depending upon the aerodynamics of the aircraft. Alright, it is depending upon the drag polar of the aircraft. Okay, now let us begin with an example here. Now find or calculate minimum glide angle, that is gamma minimum, and maximum range measured along the ground by the same aircraft that we have been considering since our first lecture, by same jet aircraft. Alright, in a power of glide at an altitude of 10 kilometers. At an altitude of 10 kilometers. So what we need to do here, we need to find first of all what is that L by D maximum. Okay, remember we have already plotted this power available, power required curve for at sea level and as well as at 10 kilometers. Also we calculated rate of climb at 10 kilometers, right? So what we need to do here is we need to see what is the L by D maximum. Alright, and then we can find, or we can also use the similar method that we have been discussing before, that find CL at 10 kilometers. This will be 2W by rho, density at 10 kilometers, area and velocity, that is at 10 kilometers V square, and then we will be finding CD at 10 kilometers, that is CD naught was constant, K was constant, and CL we just calculated. So this is CL at 10 square. Alright, and then we will simply divide this CL 10 divided by CD. Fine. Okay, now once we have this CL by CD, then we can easily use this equation, gamma minimum equals to tan inverse upon CL by CD maximum. Okay, then once we have gamma minimum, then we can easily find what is the maximum horizontal distance the aircraft can travel, because the altitude is given already. So h into L by D maximum, and you can easily find what is the maximum range. Now let us look at in MATLAB. So this is the MATLAB code that we had written before for rate of climb. So I'll be continuing from the same code. Alright, I'll just revise what we did here. We have written here the already given values: weight, wingspan, wing area, zero lift drag coefficient, that is CD naught, E Oswald efficiency factor, aspect ratio, and induced drag factor K. And then we have written two densities at sea level 1.225 and density at 10 kilometers 0.4135, and we created two velocity vectors, velocity at sea level and velocity at 10 kilometers. This we actually used this equation that we have discussed in the earlier classes, Alright, V into square root of rho SL by rho at 10 kilometers. Then the method remains same. The power required at sea level, similarly power required at 10 kilometers, thrust available which was actually given, and thrust available at 10 kilometers. Alright, and then we found out what is the rate of climb at sea level, that is in meters per minute. Similarly, rate of climb at 10 kilometers, that is meters per minute. Now what I did next was I added this aerodynamic efficiency at 10 kilometers. Alright, as I discussed, here I have written CL at 10 kilometers 2W by rho V square S, where rho 10 is the density at 10 kilometers, velocity is the velocity at 10 kilometers, CD at 10 is CD naught plus KCL square, then CL by CD, CL CD equals to CL dot divided by CD 10. Remember what was this dot? So this was, yes, this was element to element multiplication. Alright, so this both are actually vectors over here. Okay, and then I found what is the maximum CL CD, okay, maximum of this value. Alright, and after that I have written just equation here, gamma minimum, that was A tan inverse or tan inverse of 1 divided by CL by CD maximum. And obviously MATLAB gives the values in radians. I have converted to degrees, so that we can do by using rad to DEG, radians to degree. Alright, so this value will get in degrees. Fine. Now what is the maximum horizontal distance? That is R equals to H, that is the altitude, that is kilometer. So I have not converted into meters, it is in kilometers. So we'll get answers in obviously in kilometers. So H into maximum CL by CD that we have calculated over here. Alright, rest of the code remains same. I have not changed. Alright, now if I run this code, now what is the glide angle that is required? Let us have a look. So these are the plots that we have already plotted earlier. Alright, now what is the maximum CL by CD? So since I have not put here semicolon, so I have got here maximum CL by CD equals to 16.8619. Alright, so maximum CL by CD got is 16.86. Okay, now gamma minimum equals to, gamma minimum, if I see in this workspace, gamma minimum is here. So 3.394 degrees. So the minimum gamma should be 3.394 degrees to travel at maximum horizontal distance. Alright, and what is the maximum horizontal distance? You must have guessed by now, because this is simple calculation, 10 into maximum CL by CD. Okay, so 10 into 16.86. So if you want to look at the workspace, so this is R max. So this is 168.6194. Okay, so it can travel an horizontal distance when measured with respect to ground, that is approximately 170 kilometers. Okay, so if for some reason the engines fail, and if the aircraft is at an altitude of 10 kilometers, it can still safely travel 170 kilometers provided at a minimum gamma of how much? Minimum gamma of 3.39 degrees. Alright, so this is how we calculate the minimum glide angle and the maximum horizontal distance the aircraft can travel. Alright, now let us discuss next topic related to what is the altitude or the maximum altitude at which the aircraft can travel. Alright, now let us begin a new topic here, that is ceilings. Okay, so what is the capability of the aircraft to travel or attain a certain height? Okay, how much altitude it can actually gain. Okay, now let us discuss, for example, about propeller driven aircrafts, just for example. Alright, so remember this curve, power available with velocity. So I have drawn this curve multiple times in this course. You must be well versed with these curves now. This is power required and this is power available. And remember, what was this? This was maximum excess power. Okay, this was maximum excess power. Okay, now if, for example, this was at a sea level, now if I consider a little bit higher altitude, this also we have discussed. So if this is at a higher altitude, this is power available, and this is power required. Okay, so this is at certain higher altitude. So what happened to here maximum excess power? So this is the maximum excess power, at higher altitude. Okay, this is the maximum excess power at higher altitude. So as altitude increases, we have already discussed what was the equation for maximum rate of climb. It was maximum excess power divided by weight. Okay, so as the altitude increases, this maximum excess power also decreases. Okay, so there will be a certain altitude. So let me draw another curve, that is power with velocity, and say for example this is power required and this is power available. Okay, so this is at very high altitude. Okay, fine. So there will be a certain altitude at which rate of climb, in fact maximum rate of climb, will be equals to 0. So since there is no excess power, alright, so that means the power available curve becomes tangent to power required curve. Alright, so power available curve becomes tangent to power required curve. Alright, so where velocity, say for example this is 0.1, so velocity at 0.1 is the only value at which steady level flight is possible. Alright, so let me repeat, velocity at 0.1 is the only value at which the steady level flight is possible. That is, there is zero excess power, that is maximum rate of climb is equals to 0. Alright, the altitude at which, let me write here, the altitude at which R by C max is equals to 0 is defined as absolute ceiling of the aircraft. Okay, the altitude at which rate of climb, in fact maximum rate of climb is equals to 0 is defined as absolute ceiling of the aircraft. Alright, so beyond which obviously aircraft cannot attain more height. And there is another term related to ceiling, that is we call it as service ceiling, which in fact is rather more used than absolute ceiling. So this, in service ceiling, the altitude at which, let me write the definition, the altitude at which maximum rate of climb is equals to 0.508 meters per second, or you can say 30.48 meters per minute, or you can write here 100 feet per minute. Okay, so the altitude at which rate of climb is equals to 30.48 meters per minute, so that altitude we call it as service ceiling. Okay, as I said, this term is rather more used when compared with the absolute ceiling. Thus, this service ceiling represents practical upper limit. Okay, this is the upper limit, practical upper limit of steady level flight. Okay, So if I talk about commercial jet aircrafts, the absolute ceiling is generally around 40,000 to 45,000 feet. Okay, commercial aircrafts. Okay, commercial. So if I talk about military aircrafts, military fighters, the absolute ceiling is generally around 50,000 to 60,000 feet, and it can be even more than this. Alright. So because the thrust falls slowly with altitude compared to the propeller power, jet aircrafts have higher ceilings. Okay, so jet aircraft generally have higher ceilings than propeller aircrafts. Now, how to find this absolute ceiling and service ceiling? Alright, what is the method? What is the method for finding absolute ceiling and service ceiling? Method for finding absolute ceiling and service ceiling. So remember, we already plotted rate of climb with velocity at sea level and at 10 kilometers, right? So here what you have to do is find maximum rate of climb. Okay, find maximum rate of climb. For example, at these two altitudes, say sea level and at 10 kilometers. Rather to make fine results, no, you can repeat this exercise at different altitudes. In fact, let me write here, repeat this exercise at different altitudes. Alright. So say for example 1 kilometer, 2 kilometers, and so on and so forth. And then finally, whatever values that you are getting over here, plot maximum rate of climb, that is at different altitudes with the altitude. Alright. The first point was obviously finding, we already found the rate of climb at different altitudes. So instead of that, we can find maximum rate of climb at these altitudes, repeat this exercise at different altitudes, and finally plot this maximum rate of climb with the altitude. And if you follow this way, and if I take altitude in the y-axis, so this is in meters, say for example, and this is maximum rate of climb, say for example in meters per minute. Alright, so what you get is something like this, a linear curve, almost a linear curve. So this point over here will represent service ceiling. Okay, so in this point your rate of climb will be 30.48 meters per minute. And if you extrapolate this curve so that it touches the y-axis, then this point is obviously absolute ceiling. Okay, so this point is absolute ceiling. So that is maximum rate of climb where we get 0. Obviously, that point is known as absolute ceiling. And maximum rate of climb where we get 30.48 meters per minute. That point is obviously service ceiling. So take this as an exercise. Now you have enough exercises being done in MATLAB. Now you can easily plot this between the maximum rate of climb and altitude and find this service ceiling and absolute ceiling. In fact, we'll also be doing this exercise. So you can also do in your own way of finding what is the absolute ceiling and service ceiling for our existing jet aircraft, so that we'll get to know what are its ceilings. Alright. So now that we are done with the absolute and service ceiling, next important topic is to discuss time to climb. Okay. So let me write here time to climb. Now, why do we need to study this time to climb? Alright. So, a fighter aircraft must be able to, reach at a certain altitude in minimum time so that it can reach the enemy aircraft altitude in the minimum possible time. Okay. Similarly, passengers aircraft need to reach at a certain altitude to avoid a discomfort to any passengers or avoid any adverse weather conditions or air traffic congestions. So, there the time to climb or at a certain altitude becomes an important parameter. Alright. So, this is related to obviously rate of climb. And remember, what was rate of climb? The rate of climb was the vertical velocity of the aircraft. Remember? So, let me just write here or draw the figure so that you can remember what we did earlier. Okay. So, if the aircraft is climbing with this velocity, then this vertical velocity, this was the flight path angle gamma. Alright. So, this horizontal component was V cos gamma and the vertical component was V sin gamma. Alright. So, rate of climb was the vertical component of aircraft velocity, which is simply time rate of change of the altitude. Okay. So, rate of climb in mathematical terms, I can write here dH upon dt. So, here we are interested in finding dt. Let me write here dt equals to dH upon r by c. Okay. So, here r by c is also a function of altitude as we have seen earlier. In this figure, we have just drawn altitude versus r by c. So, it was also a function of a given altitude. Okay, and dt is the small increment in time required to climb small height dh at a given instantaneous altitude. So, let me write here rate of climb is a function of altitude and dt is a small increment in time dt is a small increment in time required to climb small height dh at a given instantaneous altitude. At a given instantaneous altitude. So, what will we do? We will obviously integrate this equation, integrate above equation from one altitude to another, that is from consider h1 to h2. So, we get t equals to integration from h1 to h2 and this is dh upon r by c. Alright. So, generally we consider from sea level. So, for sea level, you can write h1 approximately equals to 0 and this equation further reduces to t equals to 0 to h2 dh upon r by c. Now, if we use maximum rate of climb at each altitude, alright, if we use the maximum rate of climb at each altitude, then t becomes the minimum time to climb to the altitude h2, alright. So, then we can write here if r by c is maximum at each altitude, so then we will get the minimum time to climb to a certain altitude 0 to h2. So dH upon R by C max. Okay, so this is the equation for finding minimum time. Now here students will get doubt that how to integrate this equation, because R by C maximum is also a function of altitude. Alright, so yes, it is rather difficult to find this analytically. So we can actually do it in a graphical way to find what is the minimum time to climb. Alright, so to find or to calculate, what we either do is to calculate T graphically. We will do it graphically. We first plot R by C inverse versus altitude. Why R by C inverse? Because we have R by C here in the denominator. So we'll be plotting R by C inverse with the altitude. Okay. Now if I plot here graphically, we'll also be using plotting in MATLAB as well. So if I write here rate of climb in y-axis, this is rate of climb inverse, and this is the altitude h in the x-axis. So we get plot something like this. Alright. So since we have integrated over here, and obviously if you integrate in such a way, then the area under this curve, will represent what? This will represent T. Okay. Area under the curve. Alright. So this area under the curve will represent the time, and if we use here maximum rate of climb at each altitude, we will get minimum time. Okay. So the area under the curve from h equals to 0 to h equals to h2 is the time to climb to the altitude h2. Now we will consider the same aircraft and find time required to climb or to reach 10 kilometers altitude. 10 kilometers altitude. Okay. In fact, you can find minimum time. Alright. Now what we have done here is, we have already calculated maximum rate of climb at sea level and as well as at 10 kilometers altitude. We can easily repeat that exercise and find maximum rate of climb at different altitudes. So let me form a table here. So here I have, for example, 6,000 feet, 12,000 feet, 18,000 feet, 24,000 feet, 30,000 feet, and finally 36,000 feet. So what I found here is at 6,000 feet and of course at sea level at 0 altitude, the maximum rate of climb we got around 2400 meters per minute, right? Remember, meters per minute. So I have got exact here 22474.4. Similarly, at 6,000 feet, this corresponds to 1828 meters. Similarly, you can convert these to meters. So here I have 2041.8, 1660.56, 1324.05. So I expect you to find it by yourself. Alright. So 1026.87 meters per minute. Then we have 762.61, and then we have 523.65 meters per minute. So have you noticed here one thing? So as the altitude is increasing, your maximum rate of climb is actually obviously will reduce, because here maximum excess power is reducing. Alright. So this is the table rather that I have obtained at different altitudes. What is the maximum rate of climb? All right. Now we'll be plotting this in MATLAB. Okay. Now let us switch back to MATLAB. Now let us write the code that we have been discussing till now for time to climb. So let me begin here the discrete data that we have used, that is the altitude in meters. Altitude in meters. Let me write here h equals to so 2474, the values that I have written earlier. So I'm forming a vector over here, 2041.85, 1660.55, 1324.05, 1026.87, 762.6, and 523.64. All right. So similarly, I have to write here maximum rate of climb. Maximum rate of climb at this altitude. So I'll write here RC equals to, again I'll form a vector over here. What is the maximum rate of climb at these altitudes? All right. So this was, let me write here, this is actually the rate of climb. This is the rate of climb. Maximum rate of climb. Okay. And the altitude here is let me write here h equals to, all right, now h is 0, that is sea level, and 1828.8, 3657.6, 5486.4, and 7315.2, then 9144, 10972.8. So this is altitude is in meters. Okay, altitude is in meters. The maximum rate of climb is in meters per second. Meters per minute, sorry, meters per minute. All right. Then we have to compute what is inverse of rate of climb. All right. So I am writing here INV underscore RC equals to 1 divided by RC. So remember, this is RC is actually a vector. So I have to do element to element division. So I am writing here dot 1 divided by RC. Okay. Now next step is to do integration. Okay. Time to climb using trapezoidal integration. So there are multiple methods available to integrate this equation. So since we have a discrete data, that is one particular value of rate of climb at a particular altitude, so generally trapezoidal integration is used. So I am using same here, trapezoidal integration. Let me write here time to climb equals, and what is the syntax for using trapezoidal integration? That is TRAPZ. Okay, and the input is actually the altitude, comma, then inverse of rate of climb. Inverse of rate of climb. Okay, let me just run this code and see where is there any problem in this code. Change folder. Yes, so it has actually run. Okay, so time to climb is actually around 9.6 minutes. Okay, so we can easily print it out here, print f. So here we have total time to climb total time to climb equals to percentile 0.2f minutes. Next line, and what is the value that it should publish? That is time to climb. So if I write here, save this and run it, and here directly I can see over here the time to climb is 9.67 minutes. All right, now we can also plot it. As I was discussing before, we can also plot it, that is plot inverse rate of climb versus altitude. So let me write here figure 1. Okay, so plot h comma inv underscore rc. So this we have been doing in the previous classes as well. All right, I hope you are well versed with these syntaxes. Okay, and this is for color of the lines, B hyphen. Then what is the line width, or even in fact color we can mention. I'm preferring writing line width over here. So line width is 1.8. Okay, and we have x label, altitude, in meters. So I'm doing here step by step so that you are becoming more familiar with this simulation software, this MATLAB. Okay, then we have y label, one upon r by c, in brackets I'm writing here minutes. This will be inverse, not meters upon minute, minute upon meters. Okay, so please do not get confused. And let me write here title, inverse of rate of climb versus altitude. We can also keep grid on. Okay, let us see whether is this running or is there any problem in the code. So no, there is no problem over here. Okay, now what we are interested here in is finding the area under this curve. All right, so of course we have already found the time to climb, that is 9.67 minutes. We can also find by finding the area under this curve. Okay, so let us see how to do that. Shade area under the curve. So what we'll do is I'll hold on the previous plot so that it does not redraw in that figure. All right, so to do that we have the code is hold on. Okay, now to shade area under the curve, we have to just write here area. Okay, and h comma inverse underscore rc. All right, next I'll write here face color. Face color, let it be for example B. All right, after that I want face alpha. So I want you to explore these syntaxes. Okay, now what is this face color, what is this face alpha? Okay, I want you to explore these. So face alpha I will write here 0.5 for example. Next edge color. Okay, edge color, let me put it here black. Okay, K. All right, fine. So this is the area under the curve. Now let me run this code again. All right. So you need not to put this in quotes, phase alpha. All right. Let me save it and rerun the code. And yes, yeah. So this is the area under the curve. All right. So area under the curve, fine. All right. Now let us go ahead and plot second plot, that is maximum rate of climb versus altitude. Maximum rate of climb versus altitude. Let me write here. Now we'll go to figure 2. Now we have plot RC, that we have used RC comma altitude, that is H, and let me write here the quotes B minus, all right, with the line width of 2, okay. And then let me write here X label and Y label. So X labels, this has automatically appeared here because of the copilot. So X label, we have a rate of climb, meters per minute. Y label, altitude. So title, maximum rate of climb versus altitude. Grid on or hold off, that's okay. We can actually, let us continue running this code. Yeah, so this was the plot that we had obtained earlier. All right, and if you zoom this, so we can actually extrapolate this curve. All right, and what is the, all right, let me see here. So this is X is 523 meters per minute. All right, so we can easily find service ceiling and absolute ceiling from this plot. Okay, we just have to extrapolate it. All right, so and how we can do that? So let me write here, hold on. So let us extrapolate ceiling values. Okay, so let me write here P equals to POLY polyfit. You can search about it. What does this do? So polyfit, I need the last rate of climb value. All right, so I need to extend that value, extend that graph from the last value. Okay, so that is why I'll write here what is the vector that I need. I'll write here end last vector till from the last, second last to last. All right, this is the one, and plotting with H. Then here also will get plotted from second last to last. Okay, so end minus 1 to end. All right, let me write here comma 1. So this is the linear fit. Okay, so I need you to do a little bit research about it. What does this mean? So this is a linear fit curve. Similarly, RC is service ceiling. Where is your service ceiling? It is actually at 30.48 meters per minute. Okay, now H underscore service equals to poly, POLY VAL, polyval, that is P comma RC underscore service. So I need you to research about these syntaxes. Polyval, what is it exactly doing? You must have already got an idea that this is actually extrapolating the curve. You will see after the final results. ABSOLUTE H absolute equals to again polyval, POLY polyval. All right, and what is the value? P comma 0. Okay, that is the maximum rate of climb is 0. Okay, so do not get confused over here. Yeah, this is the absolute ceiling. Absolute ceiling over here. Okay, and let me just save it and run this code. All right, so it has already plotted it has already found these values. I just need to plot it in the graph. All right. Now, since I have already done this, let me write this code from here. Plot ceilings, plot 0 to RC till end, and H absolute till H end, and this is the color of the line width and 1.5, and I am drawing a line over here till H service. All right, let me save it and run this code. All right, now this is the altitude. You can actually see over here. If I zoom here, all right, so this is here, it is actually 0. The absolute ceiling is 14,980 meters. All right, and here, let me just a little bit zoom out. Okay, all right, so let me just zoom out here and point my cursor here. So here we have intersection curve. So this is the service ceiling, that is where the service ceiling is at about 30.94 meters per minute, and service ceiling is about 14,743 meters. All right. So in today's class, we have discussed about the gliding. What are the parameters that are depending upon the glide? So in today's class, we have discussed about a gliding flight. What is the absolute and service ceiling? How to find absolute and service ceiling? And finally, how to find the time to climb. All right. In the next class, we'll begin a new topic, that is range. Thank you.